Hello. So what we're going to do here is try and find the antiderivative of the function x to the n. And in particular, we're going to look at the case where n equals -1. Find the antiderivative of x to the -1, which is a little bit tricky. Finding the antiderivative x to n isn't so tricky though, and finding its derivative is probably the simplest thing. In fact, if you're going to remember one thing from calculus, this will be the very last thing you forget about it. This will be the one. Everything else will go. The derivative of x to the n will remain in your memory longer than anything else. So what's the derivative? In order to find an antiderivative, it's helpful first to find the derivative. So the derivative of x to the n, well, you simply multiply by this n, then you subtract 1 from the exponent. And of course, we can determine this by the limit definition of the derivative, but it gives us this simple law so that we get the derivative being n times x to the n minus 1. So, of course, that's pretty easy, but we're looking for the antiderivative. And anti comes from the Greek meaning against. So in order to find the derivative, we went this way. We want to find the antiderivative. We're going to reverse that and try and undo that process. We're going to go against it and go this way. And in order to go this way, you could see if I wanted to go from this function here to this function, I'd add 1 to the exponent here, and then I'd divide by this n. So using that same process, I can find the antiderivative of x to the n, and it's going to be x to the n plus 1, where I just add 1 to the exponent here, and then I divide by this value in the exponent. And now you're going to want, when you find antiderivatives, you're going to want to check them if you're not completely sure. So let's go ahead and check this since we're just trying to figure it out. So we take the derivative of our antiderivative. In this case, we would multiply by that exponent n plus 1, and then we would subtract 1 from that exponent to get the minus 1 in that exponent. So of course that n plus 1 on the top and the bottom are going to cancel out, and that plus 1 minus 1 is going to cancel out, and we're just going to end up with x to the n, which is excellent because that means when we took the derivative of our antiderivative, we came back to our initial function, which means that our antiderivative checks out. However, this antiderivative does check out, but there is a little bit more general antiderivative to find here, and you can see this if we just added 5 to this antiderivative. Let's say we added plus 5 to it, and we took the derivative of it. Well, that derivative of the 5, of course, is just going to go to 0, so we still end up with x to the n. So while what we just found was the particular antiderivative, we know that the more general antiderivative is going to include that plus c on the end. And you can see this graphically if you take the function f of x is x cubed here. Now, if we just added 5 to it, you can see that it certainly changes the function. However, all it really did was just shift it up. It just shifted from here up to there. If we do minus 5, it just shifts it down. So if we look at the slope at any given point, these dashed lines just kind of indicate the slope. You can see that for any given x value, the slope is actually going to be the same for all these functions. And of course, our derivative is just the slope of the function. And since you can see, since the slope of these is all the same, shifting it up or down doesn't matter, and that's where we get our general antiderivative from, because that shifting does not affect the slope, which is the derivative. So now let's look into this specific case where we're trying to find the antiderivative of x to the -1, or n value is -1. Well, finding the derivative, that's pretty simple. Use the standard rule, multiply by the exponent, and then subtract 1 from it. We just end up with -x to the -2. So that was easy. Going the other direction, not quite as easy. If you apply that standard rule that we found above, and you just add 1 to the exponent and divide by n plus 1, unfortunately that gives you x to the 0 over 0, which is undefined. So basically that rule, our inverse power rule to get the antiderivative here, breaks down at this point. It does not work for n equals -1. So let's try something else. Well, we do know that the derivative of natural log of x is 1 over x. And you can find that through implicit differentiation in differential calculus. But since we know this one, well, now if we know the derivative of this function is 1 over x, then we know the antiderivative should be close, right? So let's try that out. Let's just say we kind of undo that process and say if the derivative of natural log of x is 1 over x, then its antiderivative of 1 over x must be natural log of x. So let's look at the graph of this to see if it works out, just to kind of test it out. So first let's plot out natural log of x. So here I have f of x is natural log of x. It's this orange line here. Now I made this little function here that shows me the slope at any given point. So if I turn this on, you can see that this purple line here is just kind of showing me how the slope changes as I change my x value. And you can see that this slope, it starts off when x is close to 0. It starts off really steep, and now it's going to get less and less steep as you get higher in x value. And our derivative, DESMOS can actually plot out the derivative. So I can just do f prime of x, and it's going to go and plot this out. And so you can see that it kind of matches up, because when my x value is really small, I'm getting this really steep slope, which means my derivative is going to be really high. But when I get bigger in x value, well, my slope's going to decrease. As you can see, my f prime of x is decreasing here. But you can see that it is always positive. This slope is always going to be positive. It's always going up with natural log of x, and similarly, the value of this derivative here is always positive. So that matches up to what we'd expect. So let's see how this matches up to 1 over x. So we can go ahead and plot that here. G of x is 1 over x, and so it matches up exactly on this side. However, we run into some issue on the left side here. You can see because this derivative here of natural log of x, f prime of x, is not defined on this left side for the domain x is less than 0, because natural log of x is not defined there. So this creates a bit of a problem. So we can't actually use natural log of x. So unfortunately, it appears that our proposed antiderivative natural log of x isn't actually going to work. And the root of this problem, as we just explained graphically, is that the domain of 1 over x goes from negative infinity to infinity, excluding x equals 0, while the domain of natural log of x only goes from 0 to infinity. So the domain of natural log of x only sort of takes care of that right. Everything that's right is 0, and we have that whole left part that natural log of x doesn't help us with. So unfortunately, we're gonna have to go ahead and not use natural log of x. The bad news, good news though, is we're getting close. We're making some progress. So imagine if we're trying to get that other side of the domain. So let's just define f of x as sort of a piecewise function. So it worked great for x is greater than 0, so let's keep that the same. F of x is equals natural log of x for x is greater than 0, but we want to get in that part for x is less than 0. So if we throw in this other part of the piecewise function on the left side of the domain as natural log of negative x. And let's see how this looks graphically. We define that this is our part on the top here, natural log of x, and we'll call f2 of x that other part of our function, which is the left side. So this is kind of how we defined it above. Now let's take the derivative. We can plot out the derivative of both sides here, like this. And now that we plotted out those derivatives, let's go ahead and turn these ones off. And now let's see how well the derivative of this piecewise function matches up to our function g of x is 1 over x. So you can see they actually match up perfectly. So it looks like we're on the right track here. If we just have to define f of x as sort of two different functions. And a little bit easier way to do that is just to call it natural log of absolute value of x. It's just a simpler way to essentially write the same thing on the left. And you can see why that's the case, because when x is greater than 0, you're not changing x at all. It's the same thing as natural log of x. But when x is less than 0, for that bottom part, the absolute value just switches it over. So writing the absolute value of x here is just a simpler way to write that piecewise function on the left. So now, as we've confirmed graphically, we do have our particular antiderivative, which is of the function x to the negative 1, which is going to be natural log of absolute value of x. And of course, our general antiderivative, we're going to go ahead and add a plus c on there, just like we did before. And in this case, there's actually another way you could write this general antiderivative, and that's calling this natural log of c, this capital C times x. And you'll see this come up in a lot of problems throughout the course, so I wanted to throw it in here. And let me tell you why we can do that. If we can just look at it graphically. So this is my function in the red. F of x is natural log of absolute value of c times x. And I'm going to go ahead and turn the slope on here just like we had before. So this is going to kind of just show us what the slope is. And if I change c in here, you can see all that really does is it shifts my graph up and down. It just shifts it vertically. It's essentially it really is the same thing as adding a constant to the end of it. Adding it in the middle essentially does the same thing. So as you can see from this, it's not going to affect the derivative because adding c in the middle does not affect the slope. So therefore, we've shown that this natural log of absolute value of cx is another way to write the general antiderivative. Although it's not common to write it like this, it's good to know that actually works. So in conclusion, we've shown the antiderivative of the function x to the n, and then showed it in its special case for x to the where n equals negative 1, where our typical process doesn't work. We have to refer to the natural log of the absolute value of x as the antiderivative for that particular case.